Start recording. Yeah, let's begin. For the fifth meeting today, we'll sort of like revise a little bit how to use density metrics in the postgraduates of quantum mechanics, and just overall how to compute reduced density metrics. Um, So previously we mentioned that for density metrics, uh, the formalism is useful when your preparation of your system is sort of like having all sorts of random examples of pure states. Then instead of looking into your system as a quantum system, it's easier for you to deal with it as a classical mixture of all these statistics together. Um, our sunlight is one example because you have so many different atoms emitting the light in different polarizations. So in that case, instead of using quantum treatment, it's easier to use density metrics to sort of like consider it as a mixed state. The second one is when your physical system is entangled with one another. Then when you perform what we call as a partial trace, the reduced density matrix will be a mixed state. So here I try to provide a clearer motivation why you cannot do it with just a state vector. So if let's say you have a Bell state um, with equation 84, for example, then this particular description, especially for the first qubit, it basically tells you that when you measure from the computational basis or the Pauli Z basis, you have a probability of half to get either 0 or 1. So in this case, this is what we call as a quantum treatment because we can write it in the state vector form. And the probability half is actually given by the probability amplitude. So in this case, it will be just 1 over square root 2. You square this, and you get probability equals to 1 over 2. You get either 0 or 1. So once you measure the first qubit as the 0, for example, then the second qubit has to be 0 due to entanglement. Or if you measure it to be 1, then the second qubit has to be in the 1 state, again due to entanglement. So if let's say we want to describe this particular quantum state for just qubit A alone, so how would we try to describe it? So we might tempted to just write, oh, okay, for qubit A, basically we can write in this form. But this is actually not the correct description because even though when you write in this form, equation 85, it will give you correct statistics when you measure in the Pauli Z, which is the 0 and the 1. But then if you measure in the Pauli X axis, which is the plus and minus, and we obviously know that this whole thing you can write in terms of the plus basis. So then it gives you the wrong statistic because when you perform this kind of measurement, uh, you have 100% of getting the plus states. Whereas for the Bell set description, it doesn't matter which basis you are trying to measure, you always get probability half of getting one of it. So that's why state vector formalism does not completely describe the classical statistical example aspect of mixed states. And previously, I give this particular example. So if you consider this as a statistical measure between the left and the right circularly polarized photons, um, so it doesn't matter which kind of polarization you try to measure, it always gives you probability half because this particular density matrix is a maximally mixed state. So it gives you the motivation of why you really need density matrix to describe mixed states because there is some classical aspect of it hidden within your quantum state, and then there is a quantum aspect of it within how you formulate your state vectors over here. So the first part over here, this is classical, and then hidden within your state vectors is quantum. So over here, I mentioned regardless of what kind of measurement basis you are taking, you always get the probability of half, either the left, right, or the horizontal or vertical. This is only true for maximally mixed state because you have no information on the system at all. So then let's get back to the postulates. The first postulate is where is your state space. So of course your state space is still the Hilbert space, but now you describe it using density matrix. So the trace is 1 and it acts on your state space of a system. The second one is the evolution of a closed quantum system. So instead of using something like this, so now we use unitary matrix in this form, whereby the left side is unitary, the right side is U dagger. So you can think of it if it is your pure state. So when you act on your density matrix, so the left side actually acts on the cat, and then the right side acts on the bra, which is why you need your dagger operator over there. But of course, equation 87 is a general form because you are taking a general density matrix. So the third postulate tells you that your measurement, the probability of getting a certain measurement outcome with the measurement value m is given by this particular trace. And after the measurement, right? So you notice that this particular form is exactly the same as above. So you have the left side having your measurement operator acting on the density matrix, and then the right side of your measurement operator, you put a dagger over there, and then the bottom part is basically your probability of getting that particular outcome. But again, this is a measurement for a very general type of measurement. Usually we don't need to do that. Usually we only use projective measurement. And projective measurement has this very simple structure. So previously I mentioned that let's give this particular outer product as your projector for a particular measurement outcome M. Then we know for sure that your P dagger MP is equals to PM because basically you have something like this, right? So that's why when you perform when you calculate the probability for getting a measurement outcome M, um, this is basically what you need to calculate because now you have different psi. Remember your definition of uh, density matrix is basically pi and then psi I, psi I. So you have different preparations. That's why you need to account for it by having the probability pi over here. And of course, you can try to reverse the whole process to reformulate equation 88. So previously, we know that the definition of trace is basically summing up with your J basis, and then you perform this kind of operation. This is a definition of trace. So if you begin with this is particularly how you calculate the probability for getting the outcome M. So you add in one complete relation. So this is equals to identity when you sum with all J. And then you swap the position so that you get something like this. So this is a definition. So this is something in the middle. This is a definition of trace, right? So you see this particular structure, the J cat bra J over here, and then cat J on the other side, and then you sum over all J. So now what you need to do is to to separate out the index. So the sum with all I pairs with this operator, which gives you back your density matrix. So this whole part is your density matrix, and then you get back your definition of trace, and that is why you get a trace of row M, and then we know that trace of AB equals to trace of BA, and that's how equation 90 is equivalent to equation 88, provided that you are using projective measurements. So if you want a more general transformation, like how you would find the expected value for measurement. So this measurement contains all the possible, contains all the possible measurement outcomes. Or you can write something like this, right? So if you want to do this following the whole argument over here, you can, and it's more or less similar. It's just that now you have another summation with index m. Of course, outside you also have another term m. So you can basically derive the same equation, equation 91, the expected value for a measurement m, using the same approach as what I show here in equation 90. So if you want to do it, you can do it later. But the next part is on the postulates 4, which is how you would uh, describe the composite quantum system using density matrix. It's very easy. The Hilbert space is still the tensor product of each other. And then the joint state will be given by the tensor product of all the density matrix. So now we sort of like reformulated the whole postulates of quantum mechanics using density matrix formalism. And now you might have some questions. If let's say you have a density matrix given by this form, I can also rewrite it using a different basis. Let's say A and B. Obviously, they are orthogonal to each other when you, uh, sorry, they are not actually orthogonal to each other. Let me think a bit. Uh, you need to perform this. So let's see if they are orthogonal to each other. I forgot to check. Mm. Zero, 1, 0, 0. They are not orthogonal to each other. But let's say you can prepare in a different set of system, and you can actually see that they give you the same density matrix. So in this case, it depends on how you are performing the measurements or how you would prepare the quantum system in a different mixture, so to say. Because now you have different examples and they give right to the same density matrix. So you may try to ask how these two are related to each other. So in this case, density matrix, it doesn't really give you a very unique decomposition. As long as these two so-called state vectors, they are related by a unitary matrix, you can actually get the same density matrix. They are actually the same. So they give you the same density matrix. So the way for you to see this is basically why it is related by the unitary matrix. If you recall unitary matrix, they sort of, okay, in the book by Nelson, they basically give you more complicated derivations by using equation 96, and then you try to formulate your density matrix. So you first write in this form, and then you try to decompose it. Um, so something like this. So you basically substitute this particular equation into here, and then you have the other one, and then you have ij dagger, something like that, and then you try to proceed the calculations, and in the end, you find that they indeed give you the same density matrix. But over here, a more intuitive answer, in my opinion, is that your unitary matrix basically just rotates your state vectors. So as long as your state vector rotates accordingly, it doesn't really change the length of your state vectors for unitary matrix. And that's why whenever they are related by the same unitary matrix, it is where you get back the same density matrix. So in my opinion, this is a more intuitive uh, proof to that this theorem, so to say, if you don't want to go through the mathematics. So here we covered all the postulates. What is more important is on the reduced density matrix. This is where I want to spend slightly more time. So suppose you have a quantum system A and B, and they are given by the density matrix rho AB. So the reduced density operator for system A, so let's say your A here, this is your B here. So you have the joint quantum state, but now you just want to look at the quantum state for subsystem A. So this is what we call as the reduced density matrix, and it is given by this particular formula. So rho A will be the reduced density matrix. And then whenever you see rho B something, this is what we call as partial trace. And partial trace, you can operate as such. So let's say your density matrix is given by this. So usually when we write 0, 0, sorry. Usually when we write something like this, we meant the first qubit tensor with the second qubit. So in this manner, you try to separate out as such. So this comes from subsystem A. This comes from subsystem B. When you partial trace B out, you basically leave the A contribution. So the A part, you leave it there, and you perform trace on the B part. And because we know that the trace operation is equivalent to something like this. So in this case, your trace is B1, B2. So what you need to do is sum of I, and then I, B1, B2, I, right? And then this whole thing, let's say, I set it I, B1, sorry, B1. This is equivalent to canonical delta of I B1. So only when I equals to B1, then your inner product becomes 1. So then in this case, this particular trace boils down to B2, B1. Which is why in the end, you see over here, you have the inner product of B2, B1. So that's how you would perform partial trace. So now I have two questions. The first one, let's say you have a Bell state. Try to find the reduced density matrix of the second qubit. So let's say this is qubit A, this is qubit B. So this time you need to partial trace out qubit A. So then the kind of steps that you need to follow is that you start with rho AB equals to psi AB over here. Then the second step is to perform partial trace on the first qubit and find the answer. So this is for question 1. For question 2, try to show that the reduced density matrix of this particular system is a pure state. So maybe I give like 5 minutes to solve this. So I'm switching to a new page just to write this down. So row AB will be given by this. So this will be half. Then you multiply as usual. So you have 0, 0, 0, 0, 1, 1, then 1, 1, 0, 0, 1, 1, 1, 1. So you need to find row B. So this will be partial trace A, row AB. And now because you are partial trace out subsystem A, so you need to compare the first index. If they are the same, then you keep it. If they are different, then you delete it. So this one, it doesn't appear up when you do a partial trace. This one does not appear when you do a partial trace. So in the end, you have something like this, 0, 0. Then you have tensor 0, 0. I should put this in front. So this is subsystem A. This is B. So over here, you can see that this is just 1/2 of your identity. And this is again what we call as the maximally mixed state. So it means that you don't have any information about the system. So whatever kind of basis or like measurement preparation that you are trying to do, you can't get any information out of this particular uh, reduced density matrix. Whereas the second example that I give just now, with the A and B as this one, this is not maximally mixed because it doesn't equal to identity divided by 2. So that's why you have some preference of your measurement basis or quantum system or the preparation that can give you some information about the system. So how mix of your density matrix it sort of like reveals what kind of information that you can extract out of it. So before I continue, the second part would be if let's say you have a pure state of this form, and can you show that let's say your row A is a pure state? So this is the second question. So again, the first thing you need to do is to form the reduced density matrix. Oops, sorry. Something like this. Then you can sort of like separate out between A, B over here. So I can write A tensor with B, B. Then the third thing you need to do is to partial trace out B. And as you can see, you get something like this. Then you partial trace out B. And this equals to 1. That's why you get back this. And this is the definition of pure states. That's why the partial trace will give you a pure state. So it might sound very difficult to compute the partial trace. So let's look at what happens in general. So let's say you have a 2-qubit density matrix. If you really try to compute out the the whole matrix form, you will see that this is 0 0. Sorry, this particular entry is starting from 0 0, and then 0 0 0 1, 0 0 1 0, 0 0 1 1. So if you can't see why, you try to let 0 0 to be equals to this up until 1 1. It should be 0 0 0 1. So then this is 0 1, sorry. This is 1 0 0 0, 1 0 0 1, 1 0 1 0, 1 0 1 1. So over here, I'm just listing out all the bases. So now let's say you want to find row A. So you need to partial trace out the contribution of B. So this is where you look at the second index. If they are the same, you keep it. If they are not the same, you delete it. So that's why row A will be equals to something like this. Uh, so the first one you get 0 0. So this contribution plus with uh, let me try to have a look. The first one is 0 0 and this contribution. So you get these two contributions into the first term over here. Then the second one, if you sort of understand what I'm trying to do over here, I'm trying to show you which term actually goes into the reduced density matrix of subsystem A. The second one will be 0 1 1 0. Wait, sorry. 0 1 1 1 plus 0 0 1 0. The reason why these two are being selected is because the second term is the same, and the first one has to be the cat 0 outer product with the bra 1. Then the third one should be 1 0 0 0 1 1 0 1. So again, look at the second term, they are the same. And then the first one, the cat has to be 1, the bra has to be 0. The last one is 1 0 1 0 1 1 1 1. So you can identify 0 1 1 1, 0 0 1 0, 0 0 1 0, 1 sorry 1 0 0 0 1 1 0 1. So this is for row A. You can identify like which of the terminologies will go into row A. And similarly, you can try to identify row B. So this will be trace of A, row AB. If not mistaken, this should be the one. 1010, and then 0001, 1011, 0110, 1110, 0001, already done. 1011, done. 0101, this one. So yeah, so the purple one should be goes to row B, and then the blue one goes to row A. So that's one way for you to find the reduced density matrix faster if you can pinpoint your outer products. You can do it for 3 qubits as well, but for 3 qubits, let's say you start from row A, B, C. If let's say you want to find row C, right, then you need to perform partial trace twice. So you need to trace out AB to find row C. So in this case, you partial trace out A first, then you partial trace out B. So you need to perform partial trace twice. There are ways for you to make the whole process faster. You see that in the quantum teleportation part. So roughly speaking, this is how you would calculate your reduced density matrix. So the last part of this discussion basically goes into quantum teleportation. Specifically, people always say that with quantum teleportation, you can send information faster than speed of light, and that's actually not true. So let me just briefly describe what quantum teleportation is. Essentially, you have two parties, Alice and Bob. Initially, they share a pair of entangled qubits in one of the Bell bases. So in this demonstration, I'm only using the first one. So let's say this is Alice, this is Bob. So after they share their qubits, Bob maybe flies to another planet, and then Alice stay on Earth, sorry. And then Alice now has another qubit C that she wants to send to Bob through this pair of entangled qubits. So this is Bell state. Okay. So how Alice can do this? The first, so this is a quantum circuit. Basically, you just need to perform a CNOT, Hadamard, and then so these two part, this is the Alice system, and this is the Bob system. So Alice has access to 2 qubits. So Alice can do whatever she wants on these 2 qubits C and A. So what Alice will do is to try to perform a CNOT and then the Hadamard gate. Then Alice perform 2 measurements. The first one is on qubit A, second one on qubit C. Depending on whether or not you get 0 or 1, you perform your Pauli X. So if it is 0, then you don't need to do Pauli X. If it is 1, you do Pauli X. Similarly, for the measurement for the qubit C, if it is 0, you do nothing. If it is 1, you do Pauli Z. So after these two, over here, right, if you see this whole diagram, you see this. This is what we call as a classical communication. And this is where you cannot really perform faster than speed of light communication, because you still need to send whatever you measured, whatever Alice measured, to Bob before Bob can do the what we call as the error corrections. So let's check on this one by one. So initially you have a shared bell state between Alice and Bob. So the qubit C is what Alice tried to send to Bob, and the whole quantum state is written by this. So Alice and Bob shares an entangled state, but your qubit C is not entangled to any of this qubit A or B. So then you can expand this whole quantum state into 103. So now you perform your C naught. So after the C naught, so okay, there's a bit of you need to be slightly careful. So I mentioned CAB. So the first qubit has to be qubit C. Second one is A. Third one is B. So this is uh, slightly not the same as what we would write our quantum state. So you need to be careful over here. So after the C naught, basically your qubit C controls what happens to qubit A. So 0, 0 do nothing, 0, 1 do nothing, 1, 0 you change to 1, 1 you change to 0, and then you perform Hadamard. And this is something quite messy because your Hadamard, uh, okay, it's not as messy yet. Your Hadamard basically goes to qubit C. So if it is 0, then you go to plus, this is plus, this is minus, this is minus. Then you expand everything, plus, plus, minus, minus. Then you write in terms of the 0, 0, 0, 0, 1, 1, 0, and 1, 1 kind of thing. After that, what you need to do is to focus on Bob's qubit. You try to write down Bob's qubit in terms of a combination of alpha terms and the beta terms. The reason why you do this is because eventually you will realize that your qubits from Alice, C and A, so these are the qubits that Alice can access, will become 0, 0, 0, 1, 1, 0, and 1, 1. And that's exactly why you need to perform these measurements. So a combination of MA and MC will tell you what kind of Pauli corrections you need to perform on Bob, so that you can get back the original information over here. This is the original information that at least want to send to Bob. Okay. So looking at here, when you perform your quantum measurements, you will do appropriate Pauli corrections with Bob's qubit. So if you get 0, 0, basically you do nothing. If you get 0, 0, you do nothing. If you get 0, 1, then you need to perform Pauli X. 1, 0, Pauli Z. 1, 1, you do Pauli Y. So why Pauli Y? Because X multiply with Z. Basically, you will get something like a minus IY. In this case, this is what we call as a global phase. And it doesn't really affect your measurement outcome, which is why usually people just say Pauli Y. In my case, I write Pauli Y up to a global phase. So that's how you do quantum teleportation. So now how can we really show that there is no information that you can send to Bob through this Bell entangled state? The way to do it is first you identify what would be the density matrix for your size CAB. So in this case, I copied from here, equation 105, but I erase all the A, B, and C. So this should be CA. This whole thing should be B. Similarly to other cases. So what you need to do is to first find the density matrix of this state, and then you trace out Alice's system to find the reduced density matrix of Bob to be a maximally mixed state. So if the density matrix of Bob is a maximally mixed state, it means that there is no information on Bob's system unless Alice actually tries to send in some classical information to tell Bob what kind of Pauli corrections that Bob should perform. So this is something that you can do it later on yourself. Um, so once you verify this, it shows that uh, Bob does not have any information on this or how Alice prepares the qubit C. So that's why Alice cannot use quantum teleportation to send information faster than speed of light, because there is this layer of classical communication that Alice needs to send to Bob so that Bob knows what to do to his own qubit. What else should I say? So in the end, physically, what is partial trace? You can consider it as averaging out the contribution of some subsystem over the other. So partial trace really tries to averaging out, in this case, the contributions from Alice qubit C and A, and just focus on what is happening on Bob's qubits. So that's essentially the physical idea for partial trace. If you want to verify all this, I did some calculations. If you let the 4 possibilities as B1 until B4, your first reduced density matrix should be given by 107, and the reduced density matrix for Bob should be given by 108. Yeah, I think we don't have that much time, so I will just stop the recording now. And any questions?